We come at last to the culmination of this this part of the exploration of infinity as the size of a set of objects. And in this video, we'll see that there are different infinities. There are infinities that are larger than others, demonstrably larger. And so let's get started. The hero of our moment is Georg Cantor, German mathematician, lived between 1845 and 1918. And these were initially his ideas in the late 19th century. Some very unsettling ideas. He was the first mathematician that really seriously studied infinity. Others, he did not make a lot of friends with this because he unsettled a lot of people, but there are mathematicians even in his day who took up his work and advanced it forward. All right, so here's the idea. We talked about in our last video the notion of countability and showed how Cantor was able to associate the set of counting numbers with all the positive fractions through a diagonalization argument. And so it really showed that there are as many fractions as there are counting numbers. Pretty startling result. And so Cantor said, okay, let's look at something like this. Now this is not exactly what Cantor did, but it's very close to what he did. So he said, well, let's look at all the decimal numbers between 0 and 1, which have this form. They just have ones and zeros in them. We won't look at all the decimals, just the ones with nothing but ones and zeros in all their decimal places. He said, let's take the set of all of those. Let's take that entire collection of these numbers. There are, of course, infinitely many of them. He said, look, we can count these. We can do a diagonalization scheme where we take the first number, the first digit of the first digit of the first number and match it with 1. And then 2 and 3 will be second digit first number and first digit second number. 4, 5, and 6 will be third digit, second digit, first digit. And then 7, 8, 9, 10 will be 4, 3, 2, 1. He said we can diagonalize this set of numbers, this infinite set of numbers, and show that it's countable. It has the same size as the natural numbers. So far, so good. It all seems quite reasonable. But then he says, but wait a minute, we have a little problem here. Suppose that I'm going to build a number, construct a number, with nothing but ones and zeros. By doing this, he said, let's take the first number and we'll change the first digit. All right, so here's my new number. And because I change 1, it goes to a 0. And then we'll take the second number and change its second digit. All right, so that one also becomes a 0. We'll take the third number and change its digit. That becomes a 1. Take the fourth number, change its fourth digit. That also becomes a 1. And we'll continue this all the way down. So we'll run through that entire set, that entire collection of these numbers. And when I create this number, I find that it's not in this list. Because every number on this list is different from this because it has at least one digit that's off, that was changed. And so there's nothing on this list that matches this number because in every decimal place there's something different with each number. He said, well, that presents a problem. You think, well, my goodness, how can that be? We listed them all, but then you found one that's not on the list. Well, let's throw that on the list. We'll add that to the list. He said, well, then we have the same problem. Because when I include this new number on this list, I can go through the same argument and create yet another number that's not on the list. Because we'll change one of the digits of this number too. And it'll be different. And so no matter what you do, you can never get all the numbers on this list. You can always find one that's not on. Even though you've assumed they're all there, they're not really all there because you can continue to find new ones. It says, well, that produces a contradiction. I cannot list all these numbers. I cannot count them through a diagonalization argument because I can always come up with a new number. It said this describes a different size of infinity, a different kind of infinity. He says that size, or that cardinality, cardinality is the word for size of a set, that size is called aleph 1. So let's see, here's aleph 1. That's what he called it, this infinity, the size of this set. Now the size of the set of natural numbers, or the size of the set of fractions, take your pick, he called aleph null, and so, or aleph 0. So he was able to show that these are actually different. This infinity is actually larger than this because it describes something of a much different nature, of a much larger nature. Sets that have this cardinality or this size can be counted. These sets cannot be counted. And so this infinity is larger. He called this number C for continuum. And actually the set of real numbers, or even just a interval on a number line, say between 0 and 1, for example. The real numbers, you remember that from algebra. These are all the numbers that you can represent in decimal form. Not just zeros and ones, but all the decimals. The real numbers, that set has cardinality of C, or aleph 1. Cantor also showed that 2 to the aleph null is equal to aleph 1. So he's able to come up with some kind of numerical relationship. This is really getting pretty strange, 2 to a power. But if you study sets, you think about the number of subsets of a set is 2 to the number of objects in a set. So if you get into that, you can kind of get sort of an intuitive idea where this thing might come from. There are other kinds of infinities. There's aleph 2, aleph 3, aleph 4. You can form aleph 2, I believe, by taking the set of all subsets of a set of size aleph 1, and you create a new subset, a new set called with the cardinality or size aleph 2. And then you can take the set of all subsets of that set and create yet a set with a larger cardinality in aleph 3, and you can continue this forever. So there's a whole string of transfinite or infinities, whole string of these which are of different sizes. I'll leave you with this. Cantor came up with the continuum hypothesis, and the continuum hypothesis addresses the possibility: is there an infinity between this basic lowest level infinity and the next infinity, between aleph null and aleph 1? Is there an infinity in between? And it was finally demonstrated, I think it was in the 1960s, that we cannot prove that, whether that's true or false, whether that exists, and under the current way we do sets. And that's pretty interesting in itself. That's an example of the Gödel's incompleteness theorem, which is a topic for a whole different video. So anyway, we're done with this aspect of infinity. In the next remaining videos in this series, we're going to address the idea of infinity as a number, and this really strikes at the heart of the foundations of calculus.